offerings enabling organizations to drive next generation analytics and planning solutions. He has been actively involved in building intelligent data analytic platforms and delivering solution across analytics strategy, planning and advanced analytics with strong expertise in solution architecture and enterprise transformations. So once again, on behalf of IEI and Sri Shakti, I welcome you to this webinar, sir.
Thank you, ma'am.
We have 1 second, sir. Sendal Kumar, sir, can you start with
Yes,
the welcome address, sir?
yes. I am waiting for you to invite me. Yeah.
Yes, sir.
Thank you. Yeah, say I am Dr. M. Sendal Kumar, the chairman of the Institution of Engineers India Coimbatore Local Center. Very good afternoon to all. This IA technical webinar on AI architectures for digital twins, cyber physical systems, and scalable data engineering is being organized by the Institution of Engineers India Coimbatore Local Center under the aegis of Chemical Engineering Division Board of IEI in association with the Department of Computer Science and Engineering, Sri Sakti Institute of Engineering and Technology, Coimbatore. The IEA is a very prestigious professional body comprising over 2.6 lakh engineers from various
Hello, sir.
disciplines. Headquartered in Kolkata, IEA operates through 124
Okay,
centers
okay.
across
Sir,
India
இன்னொரு
and
வாட்டி
six
introduce
overseas
பண்ணிடுறேன்.
locations. Our Coimbatore local center has been actively contributing to the engineering community for the past 60 years. As a chairman, I am pleased to share that IEA headquarters presented the Best Local Center Award to the Coimbatore Local Center for the year 2024-25, recognizing its overall performance among over 90 centers nationally. IA supports technical activities and research and development activities also. As chairman of the IEA Coimbatore Local Center, I am delighted to deliver the welcome address for the technical webinar today. I welcome the president of IEA, chairman of Computer Engineering Division Board, members of Computer Engineering Division Board, council members, and Saurav Dasgupta, Executive IEA Headquarters, to this webinar. I would like to extend a heartfelt welcome to our distinguished panelist, Mr. Prakash Kamaraj, Senior Manager, Deloitte, Deutschland, Bavaria, Germany, Dr. S.K. Mauliswaran, Professor, Department of Computer Science and Engineering, Dayananda Sagar University, Bengaluru, and Mr. Gerald Felix, IT Analyst, Bosch Global Software Technologies, Coimbatore, who will be sharing their expertise on AI architectures for digital twins, cyber physical systems, and scalable data engineering. Then, I also wish to welcome Dr. K. Kannamal, Professor and Head Department of Computer Science and Engineering, Sri Sakti Institute of Engineering and Technology, Coimbatore, who has taken the responsibility as moderator of this event. At this juncture, I would like to express my sincere gratitude to the principal and management of Sri Sakti Institute of Engineering and Technology for their continued support and collaboration with IEA Coimbatore Local Center in organizing various events across different engineering divisions. Additionally, I would like to welcome Dr. J. Pradeep Kumar, Honorary Secretary of IEA Coimbatore. I am pleased to welcome committee members, IE corporate members, faculty, staff, and students from various institutions, as well as participants from various sectors across the country for this program. If you look at the theme of today's webinar is highly relevant in the area of Industry 4.0 and intelligent automation. So the rapid advancement of artificial intelligence, cyber physical systems, and data-driven technologies is transforming the way the industries design, monitor, and optimize complex engineering systems. So, therefore, this webinar provides an excellent platform for experts, researchers, academicians, and industry professionals to exchange their ideas, knowledge, practical insights, and explore emerging trends in AI driven digital transformation. So, therefore, to all participants, I wish an insightful and enriching experience during this webinar. On behalf of the IE Coimbatore Local Center, I once again extend my warm welcome to all of you. Thank you so much. Over to Dr. Kannamal.
Thank you, sir. Thank you for your address. So, today's seminar topic is AI architecture for digital twins, cyber physical system, and scalable data engineering. So, on behalf of Sri Shakti and IEA, once again, I welcome all the members and the representatives from IEI, Dr. Chandra Kumar sir, and Dr. Pradeep Kumar sir, and Mr. Saravanan for organizing this webinar. So, digital twine is a digital representative of the physical asset. It uses real world data, both real and historical, or machine learning models to enhance the operation and support human decision making. So, this is a very, very interesting topic. So, we are very happy to welcome our first speaker, Mr. Prakash Kamraj, Senior Manager, Deloitte from Germany. His topic is a cognitive domain, embedded generative AI and LLMs into cyber physical loops. So he is a senior manager at Deloitte. So he is having 19 plus years of experience in SAP analytics, enterprise data platforms, and digital transformation. He completed his BE Computer Science from Bardiyar University. He has an extensive experience working with global organizations including Deloitte, EI, Brilio, and SAP Labs, contributing to large-scale enterprise analytics and transformation program. He is currently leading SAP Analytics cloud offerings, enabling organizations to drive next-generation analytics and planning solutions. So, I welcome you on behalf of Sri Shakti and IEI. Our next speaker is Dr. Maulishwaran, Professor from Department of Computer Science and Engineering, Dayananda Sarkar University, Bangalore. His topic is hybrid AI models, blending physical based simulation with neural networks. He has completed his PhD in Anna University. He is having more than 21 years of experience, both from industry and the research. He has many publications in reputed journal. He has received funds from standard funding organizations for conducting various sponsored programs. Our third speaker is Mr. Gerald Felix. He is an IT analyst from BAST Global Technologies, Coimbatore. His topic is MLOps for digital twins, continuous retraining, worsening, and A/B testing in production. He's working as an IT analytics and he has completed his MBA in technology management from Anna University, Chennai, and bachelor's degree in information technology from Bardiyar University. He also holds a diploma in computer engineering with distinction. He has over 10 plus years of industry experience in IT with expertise in database management, enterprise application support, data engineering. He has worked extensively with PLSQL, Oracle databases, and cloud technologies contributing to large-scale enterprise system. He has experience in managing production development and testing environment and is skilled in troubleshooting, debugging, and root cause analysis. So thank you once again for giving me the opportunity to present about the webinar. Over to you, Prakash Kamaraj, sir, for his presentation.
Thank you, ma'am. I'm sharing my screen. Please, one of you confirm if you're able to see my screen.
Yes, sir.
Thank you. So today, the topic what I'm going to talk about is the cognitive twin, embedding generative AI, LLMs into cyber physical loops, right? I mean, this is one of the important topic in the generation of AI. Everybody is talking about AI, but not everyone have clear understanding of how AI is contributing towards the intelligent enterprise. And that's where, I'm going to talk about it. And the theme what I'm going to take today is moving from the passive simulation to productive or proactive decision making. Before I go into detail, I would like to take a small moment to thank Institution of Engineers and as well as Sri Shakti Institute of Engineering and Technology for giving me this great opportunity and to be the guest speaker and then for this webinar. And I'm really excited and I'm looking forward for the conversation with you all today. So, about myself, so it's already been told, but few words from me. So, myself, Prakash Kamaraj. I'm also natively from Coimbatore. I'm expert in bringing data, AI, cybersecurity, digital transformation for more than 20 plus years in the industry. Currently, I'm working for Deloitte Consulting GmbH, based in Munich and Germany for past close to 6 years. And I have been working with many organizations, including SAP, Brilio, EY, and Deloitte now. So mostly my life I spent in the last 2 decades in the data and then digital applications. Um, Knowing that SAP is one of the complex systems in the world, and it is one of the known system for generating tons and tons of data. And I spent my last 10 years in building the digital applications to translate the data into meaningful insights. And I'm leading the SAP Analytics portfolio from Deloitte, where I am helping the CXO suite and then operational teams to effectively translate their data into meaningful outcomes, which helps them to drive data driven organizations or decision making scenarios for the last 10 years. With that, I would like to move on to the topic, which is the Gen AI, how the Gen AI is embedding it, into the cyber physical loop. So, if you look at industry revolution is happening in every decade, right? So we all started from industry 1.0 till now 4.0, right? So now 5.0 is also in emerging, and intelligent enterprise is all about building automations, building the digital systems, producing the data, and making the systems to collect information, right? But is it really enough, right? We are witnessing the major revolution or a revolution of the intelligent enterprise, but the systems are still disconnected. The systems are still not capable enough to understand why, what, and how it is happening, especially the scenarios, right? And then making productive or proactive information to the business teams, to understand like what I should do, in case of my worst case scenarios, right? um, so that's why the Gen AI and LLMs are more important, or the digital twins or the cognitive twins are more important, to revolutionize this next generation of AI systems. And this is the idea behind the cognitive twins. And let's understand why this matters now. As you see here, okay, so most of the industries right now today in this era of industrial revolution, they all have built the digital twin systems. And the industries have spent decades of effort to build this system. If you look at, we all started from a smaller digital system, starting from Excel, so that's the first digital innovation for the industries, right? From paper to a computer, right? So from there it all started. And then today, now if you look at the well established manufacturing industries, they have the sensors, which is sending the data to the digital twin in real time, just as is, right? And then it is also having this the closed loop, right, where the systems are producing the meaningful insights out of it, right? But what are the key challenges in this, right? So most of the systems today are more of a reactive systems, right? Even the customers whom I discuss it today, they could be larger customers, they are all innovative customers, but still they are really struggling from this reactive to proactive. So there are so many dashboards. I work with a customer who has 1,000 plus dashboards, yeah. But what is the meaning of these 1,000 plus dashboards? Of course, these dashboards are important. I'm not saying that it is irrelevant, but these dashboards are only talking about what just happened. It never talks about why happened, how it happened, right? And what it could be improved, as in real time. And that's where, the real time decision making is very important, right? And the key question now we all should ask is, right, can machines make reasoning behind the data what is there today? So that is where the cognitive twin is very important. So let's see what is cognitive twin. So before we go into that, right? So the evolution of intelligent enterprise, which I talked about recently, right? We all seen this first revolution till the fourth generation, and then now the 5.0 is also in emerging, right? We all started from small automations till the datas are, getting like, millions and millions of records are producing every day. If you look at it from, the fourth gen IoT, driven connected manufacturing systems, so let's take a car manufacturing industry for an example, right? Toyota for an example, so they are generating, you know millions of records every day, right? But what is this millions of records are meaning to the company, right? So they have to improve performance, they have to improve the quality, they have to improve the supply chain, they have to improve the cost optimization, right? So there are so many factors, right? The companies would like to really understand, besides the data, what really it is stored inside the system, right? That's where, the real meaningful purpose of the AI. That's what I think, right? So when the data is giving me an insight which I can't see by my own naked eyes, then the system is more powerful than me. Okay, that's how I see it, right? And that's where, the cognitive twins are now getting evolved, okay, around the digital systems in place. And that's where, the need of cyber physical systems are there. I mean, in the current need. Yeah. So let's try to understand what is cyber physical systems. Okay, so this is not something new, so most of you should be knowing it. Yeah, so this is nothing but the systems, right? So if you look at it, there are some physical systems, which is nothing but the machines, or the IoT systems, or be it whatever it is, which is producing the data, right? So where the data is produced, and then the data is sent to a specific digital twin, where the digital twin is constantly, capturing the data, and then trying to build the insights on top of it, right? So most of the time, like I was saying, it is like, the dashboards, which is talking about why, what, and then we call it as key performance indicators, right? So most of the C-suite people are very much interested in, in the KPIs, like what happened, why happened, like, what is my this one, but basically it's all about the past information. But what the CPS, the cyber-physical systems, should be doing, or is known to be doing, is the future. Like what I should do, like how I can be competitive, and how I can improve things. This is what is going to be. But for that, we need not just data to be just in numbers, but data to be in a more meaningful, human readable, um, contextual information, right? So this is what is very important. And if you look at here, so this is the cyber physical systems, we are calling this as an closed loop ecosystems. What does it mean? The data is generated, then the data is processed, and then the data is providing information to me, and then I am taking the proactive information, then I am building the insights out of it, and then I am kind of moving towards the insight what I have received it from the data. Then again the data is produced. Okay, so this is how the loop is there, so, and that's how it should be, right? And then in between, there are so many, intelligent systems in place. Example, the Gen AI, example, the LLMs, example, the connected systems, where it is producing the information and then processing the information in real time, right? And then also the systems also should be able to process the external parameters. For an example, the COVID situation happened, right? So when systems are most of the time, in that particular duration, most of the industries are struggled, that they are not able to, you know build a meaningful system from a supply chain point of view, right? So this is like an external parameter, right? So when you have the complete visibility of your own organization or the industry data, but if you are unable to collaborate or get the insights of the external parameters of the supply chain, you know you know parameters, then it will be difficult for the industries to build the industry driven data decision making scenarios. So that's where the cognitive AI will help through the cipher physical systems. This is basically a concept where the core pillars of the industry 5.0 will be more focusing on the AI, where predictive and proactive autonomous decision making, where the systems are started building the insights and then also automatically doing something. Example, I'm working with a client where the client is building a system where they are empowering the AI to make decisions. Example, to run certain automations. Previously we call it as robotic automations, right? And then the cognitive twin, where building not just digital systems and also the AI enabled systems, where it is also providing the adaptive simulations. And of course, most importantly, the cybersecurity. Considering the digital, growth of the industry, and of course now AI is kind of blasting, with the tons and tons of data. Cybersecurity is again becoming more threat, right? So you need to have a strong cybersecurity, which is in place, to secure your data, and you're not losing any data outside world, and you're not losing any data to anybody who can misuse that. And protecting your data is very important. And human centric systems, of course, every data intelligence you are building is for us, right? That means the human should be the centric point of attention, where everything should be understandable to us and everything should be meaningful to us. I mean, so that we are able to think and then act upon that. And of course, the systems are autonomous, so where it is continuously doing its operations more optimized way. Yeah? So the question is, so like the missing piece is, like whether the intelligence is in place today or not. Most of the time the answer is no, right? The systems are getting evolved and industries are trying to achieve the next generation of cognitive systems. So let's talk about the digital twins, and what are the real limitations or the key challenges for today, right? So as I already mentioned, most of the time the industries are already having it, for an example, in the connected manufacturing industry. So the real systems are there, and then the digital twins are, kind of, processing the data and then producing the insights. Yeah, but here, is the digital twin for me explain the problems and recommend the actions at this moment today? No, right? Of course, you have today seen a lot of evolution towards the AI, a lot of GPTs in place, which is also producing so much of innovative things. So now you see, if I want to search something, ChatGPT is good, Cloud is doing magics, and then it is building application in seconds and minutes. There are so many intelligence are in place, but what are the key challenges from an enterprise point of view? And living in this SAP world, I can really understand that, and I can tell you that AI in a normal commercial mode or in the generic world, yes, it is evolved very high, right? And it is doing wonders. But when it comes to AI plus enterprise, that's where the real challenge is there. Because the AI plus enterprise, you need the AI, the intelligent capability should talk to the enterprise data. If you talk about the enterprise data, if you I mean, generally in SAP world, right, any company, any bigger companies will be having thousands of systems, not just hundreds, thousands. Okay, this is not only an SAP world and also the non-SAP world, where SAP and non-SAP, you need to combine this data to produce a meaningful outcome, right? So that is where the real challenges are there, and that is where the real limitations are there today. In this era, where the meaningful outcomes are not yet been able to produce. Of course, now with the emerging cloud, technologies, obviously, right? So now this is becoming more possible, right? So now there are a lot of cloud solutions which are coming in place, so where you can combine all the data into one cloud, example, AWS or Microsoft or whatever it is, right? Where the cloud solutions are combining all the data, and then it is helping to provide one single combined view of the data, which is going to help the cognitive AI, where the cognitive AI will be sitting on top of it to process the data, to have more reactive dashboards, and to have more pre-populated contextual informations, so where you can talk to the data. I'm underlining the word, you can talk to the data. For an example, you would like to ask a question like, why my production has low efficiency, right? Or what is my real challenge in my supply chain, or what is my production capacity in this particular unit, for an example. So these are the questions I'm just asking, like a very natural language based, right? So if your cognitive AI or if your intelligent system is able to provide such information like ChatGPT is giving you, right, that will be the success story for us. And that is what this cognitive AI is going to do. And it is not too far away. And some of the industries already been achieved. And I have implemented some of the solutions into some of my customers, and it is working in place. And then, in my view, in another couple of years, you will see that most of the companies will achieve this. So let's talk about what is cognitive twin, right? So cognitive twin is just an extension of the digital twin, right? So 90% of the industries, I would say that they have a very strong digital twin. So they have the physical systems, and they have the data, enormous amount of the data, and they have the intelligence system also in place, which is nothing but the analytical layer. So they have a lot of analytical topics in place, right? Where the data which is getting translated into the insights, right? Cognitive twin is one step ahead, where you are embedding the AI, right? For an example, the LLMs or the Gen AI capabilities. So for an example, in SAP world, we also have a lot of AI systems in place. For an example, SAP Joule is there. You can also bring your own AI to build your own AI algorithms. And there are a lot of innovations happening on that. On the other side, in the non-SAP world also, there are so many I would say that it is also very competitive, and it is also very powerful. Yeah, so where the GPTs are in place, where you are making use of these GPTs to provide like Gen AI capabilities to talk to data. If you look at most of the industries already have created the AI agents, which is kind of talking to the data. And they're able to type your questions instantly, and then try to at least gain some answers. But it is a bit challenging from the accuracy point of view. That's something we will talk later, right? But cognitive twin is should be positioned for learning from the data, right? So first thing is that, first you should be having the learning. That's where the LLMs come into place, right? So LLMs, the models, helps to understand the data, the seasonalities, the patterns, the ups and downs, whatever it is. Yeah, it is very important that the system is keep learning every second. Then explaining the insights, building the reasoning, sorry. Yeah? So the next thing is building the reasoning. Then then explaining the reasoning why this has happened like this, and creating a recommendation, right? Okay, now this has happened, and this could be your path. So this is where our neural systems will be helpful to build the paths, and building scenarios, right? With 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 a lot of simulations in place, with a lot of internal external parameters in place. And then it is also allowing us to also perform what if simulations, right? So for an example, I wanted to be ready for my future risk and mitigation plans. Yeah? And then finally, it should not be complex for me to understand. It should be as simple as it is possible, like I am doing a Google search, right? So even if I am not talking to that very well, it should be able to understand me, and it should be able to provide a conversational interaction. And that's what I call it as a key shift from passive monitoring to active operational intelligence, right? So nowadays, you also might be knowing there are a lot of co-pilots in place. So for an example, right? So there are so many co-pilots in place, and then they are also talking to the human as well as the data. So they are being the interface between the human and data, or the digital twins, right? So here, as I mentioned it already, the role of Gen AI and LLM is the key for achieving the cognitive AI in future. Of course, each of these pillars, as you see here, LLM, Gen AI, and AI agent, and agentic AI, each of them play a key role in building the next generation cognitive AI systems, right? And of course, with the help of Gen AI, so the data is converted into a plain English natural language based systems, where I don't really need to be a technical expert, right? So as I mentioned, past 10 years I was working in the digital data transformation. Okay. And if you see, most of the innovations have started from technical world to the business world, right? So there is a term called self-service, right? Self-service data intelligence system. What does it mean? Before, like 5-10 years before, any business leader who wants to understand something, they are highly depending on the technical team, or the backend team. Without their help, they are not able to build any insights. Example, so there has to be some data analyst, there has to be like data scientist, who are building so and so insights, and then they are putting in a nice PPT or chart or whatever it is, and then sending it to the business analyst, who is translating these insights to the business leaders. But this era is completely changed now. So that is where the self-service data intelligence platforms are transforming the way how the business is looking at the data without having the intervention of the IT or backend team, right? So this is already is in place, and then with the help of this next generation of the agentic AIs, or AA agents, will going to revolutionize this particular topic. But the key challenge is, what is the data engineering we should be having, and why it is important to have a scalable data engineering, right? So I mean, to simply explain, right, it is like, let's say you have different departments in an organization, finance, production, HR, and planning, so and so, right? Sales, marketing, yeah. So what if all of them are not talking to each other? They are all independently working. Will it be giving an optimized, optimized place where everything is working fine? No, right? So the key thing here is the communication, the exchange of data between these departments, right? As a simple example, right? Likewise, to have a scalable data architecture, you need to have a data layer, which is the base for the AI in the future, or the intelligent systems in the future, where the data should be flowing from systems to systems seamlessly, and the data should be able to translate and getting converted, and then it is processed by the AI without having any difficulties. And of course, this is what the real challenge today also. And most often, the biggest challenge is the quality of the data, right? So working in an SAP environment, I know the data quality is one of the key challenge. Okay, so integration of SAP systems, or even any systems, is very complex, right? So you cannot really transfer the data from systems to systems. Okay, so that's where now the cognitive AI, the data architecture layer is very important, where you have the data flowing from one system to another system, or it is going to one common system, where every data is available for you to process. And like I mentioned it previously, that's where the cloud solutions or clouds are helping, to build this data layer, with all these data processing layers, like data mesh, or data governance, then inbuilt LLMs, AIs, so now this is already as game changing topic, like the clouds. So with that, I would like to also share some of the case studies, which I also have been working in the last 10 years, in the three different industries. I would like to talk about it. The first one is the smart manufacturing. So as you all know, so most of the time, the manufacturing industry is the first one to adopt most of the innovative topics. Yeah? So if you look at modern manufacturing, or the connected manufacturing, so the IoT has created a huge revolution towards the connected systems, right? So where complete automation has been established, and the data is available in real time. Example, the companies like Bosch or Siemens, or even BMW, Mercedes, so there are so many companies who has completely automated their systems, I mean the production completely. And they have already started working towards the cognitive AI, right? Which means the example case is the predictive maintenance, right? So like predictive maintenance is one of the important topic to have the high availability and then high productivity, right? So it is already been achieved, for an example, 95% is the accuracy, right? So 95% is very good. And they also have to have a very strong root cause analysis of the failures, for an example. And systems should be able to proactively understand why it is going to fail, right? And then it can be avoided. And then and then it is also enabling the operations team, the soft floor managers, to also understand easily their data, with the simple natural language based queries. So the agentic AIs is or Gen AI based agents, is helping them. And of course, they are also proactively providing the recommendations, which is example, like build, with the help of combining the supply, production, and the other financial macroeconomic parameters, it is also giving them, what kind of path they should be going on, to have a more production optimization. They do not either want to underproduce, they do not want to overproduce, right? That's very important. Here, example, like, the next topic for the smart manufacturing is, 100% automation, so where everything is managed by AI, and AI is also making autonomous decision making. This is what they are working towards. The second use case is smart buildings. Yeah, so this also is very very interesting topic, in my view, because I was also very fascinated, when I see the transformation of the smart building. Yeah, so example, again, this is also from an IoT perspective, right? So um, see, here the examples are given like Schneider Electric or Honeywell, right? But I would like to give a simple example of the hotel chains. If you talk about Hilton or, Radisson, or any bigger hotel chains, if you take it, right? So now they have completely automated the or enabled the smart building concept, starting from energy saving, right? Or they have created intelligence HVAC systems, like heatings or ventilations or, ACs. Everything is centralized, right? It's controlled by a digital system where it is also controlling the whole physical systems, and it is also operating by itself. So why it is so important? If you look at it, most often sustainability is one of the key topic nowadays, right? So be it, water management, be it energy management, so they wanted to, if they wanted to achieve net zero goals, and they have to bring optimization in all these topics, right? So having these systems help them, to produce, or enable them, to understand where I am really having the carbon leakage, and how I can really control them, right? So this is just amazing in my view, right? And if you look at, a size of Hilton, for an example, they are a global chain and they have thousands and thousands of, hotels placed in around the world. And if they wanted to be, 100% moving towards the net zero, like carbon reduction, for an example, this is just a game changing moment for them. Yeah, so I've seen it, like, I'm whenever I travel, i've I've stayed, most of the times in Hilton, and I've seen, how Hilton has embedded all these systems in place today. Yeah. The third case is the supply chain industry, and the biggest companies you may know, Amazon or DHL, for an example, from here in Germany, right? So you all might have seen the stories around Amazon, how they have 100% optimized or automated their warehousing, right? So whenever you place an order, then the whole system is being right, completely autonomous, right? So there is no more manual intervention in this. And starting from, you know controlling the inventory management, till the supply chain systems, right? So till it is delivered to the customer, and then not only after the delivery, it is also building the analytics on top of the delivery experience. And that's why, Amazon is the best company right now. So they are trusting their systems, they are trusting their data, and they are trusting their outcomes. So they are always one step ahead of the others in the world. And that's where, they are able to gain benefit out of these such cognitive systems, right? The digital and then autonomous AI systems, right? And if you get a chance, please go and watch the videos of Amazon. There are so many videos from YouTube which is available, which they talk about how they are enabling the digital twin as well as cognitive twin for their day-to-day operations. Yeah. um, with that, I would like to close my topic for the today, right? So so today we have seen about what is digital twin, how the industry revolution has happened, of course, what cognitive AI can do, right? And then what AI can lead to, the next generation of proactive decision making scenarios, right? So this is the era of data, right? And we always often say in our organization, data is the new oil, right? So data is gold, right? But if data is not speaking to you, right, there is no point in having any digital system, right? There is no point in having any AI system, right? So data should be converted into meaningful outcomes, irrespective of where it comes from, what it tells, and what it can do, right? But having said that, still there will be, or there are some challenges in place ahead of us. Example, the AI hallucinations, right? So of course, the AI is emerging topic, and it is also like a baby, if you ask me, right? So it needs to learn a lot of things, right? It will be one day a grown person like us, and it will be more intelligent than us. There is no doubt about it. But today it is having its own difficulties in producing the accuracy. And of course, cybersecurity is another threat, right? And you would have seen a lot of cybersecurity threats even in cloud, for an example, right? So it is very important that you we are having a great governance in place, for the even AI systems. Otherwise, AI can do anything which you have no control or whatsoever it is, right? And obviously, AI doesn't mean that, yeah, everything is 100% autonomous, right? It is automated. That means humans are no more needed. No, humans are still there, and it is around the human. Okay, everything should be in place, but it is only there to simplify the work or simplify the role of us, right? And the future highly depends on the Gen AI, agentic AI, and then self-optimizing infrastructure and the autonomous operations. So with that, I would like to close my topic for the today. Thank you so much, and I'm looking forward for the Q&A section right now. Hello. Ma'am, is there any questions specific to me?
Students can ask any questions. Students, if you have any queries, please ask. Please type your questions in the chat box. Chat column, no? Here, type your message.
I think you have to post your question in the Q&A, if not chat. Yeah. Do I need any special software to implement this digital twin? No. Your digital twin itself is empowered by the softwares. Yeah. So it doesn't matter which technology you use it. Okay. What it matters is, you are able to collect the data, you're able to translate the data, for a meaningful outcomes. Maybe I take another question in this regard. Do I need any specific software skills to implement? Obviously, right? So this is not just one specific skill. Yeah. So you have so many. You have to have so many, right? Of course, not one person can enable everything, right? So there are people, who understands the data, who understand the physical systems. Yeah. So they are the ones, who are building the data architecture, and then the systems, we in SAP world call it as basis guys, who are infrastructure guys, who understands this scalable architecture. And second, the core application developers, who develop the digital solutions. Then the third one is the AI specific skills. So the AI specific skills, is required to build the cognitive AI twin. Yeah. The second question is, for cyber physical systems, latency is critical. How do you balance the need of complex AI processing in the cloud requirement, cloud requirement for millisecond level response times for the physical edge system? Yeah, of course, this is the key challenge, like I mentioned it. See, like I was saying, it's like a closed loop, right? So it's not only that, you are sending the data and then you are processing the data, but how the data is sent back to you in the real time is very important. Um, if you look at it in an SAP world, I may not be expert in the non-SAP world, but in the SAP world, SAP has their own ecosystems in place. Yeah? So even they have the integration with the cloud solution. Um, the data is moving between the systems almost in real time. We call it as live streaming of the data, right? So this is like helping in the SAP ecosystems or SAP world, that the data is moved into real time, and the data is streamed in real time, and then the digital twin or the AI is in place on top of it, and then producing the real time insights instantly. Yeah? So but it is also the similar concept in the non-AI, non-SAP world, such as the AWS or Microsoft. Then third one is, how does IoT support the digital twin? Of course, IoT is the heart of the digital twin, right? So without you having the IoT, you will not be able to produce the data, right, in real time. So IoT is the heart of the digital twin, and you should be having it in place. Any other questions? So I'm also happy to connect you all in LinkedIn. So you have my LinkedIn profile in the first page. So, or otherwise you can search my name, Prakash Kamraj, in the LinkedIn. Please connect with me, and I'm happy to talk to all of you in this space. Um, Even not today, but beyond today also, I would like to connect all of you. Thank you. And if no further questions, ma'am, you can move to the next topic, or we can wait. Yeah.
Thank you, sir. Thank you for your insightful presentation. Now I request Dr. Maulishwaran to handle the session.
Good afternoon, ma'am.
Good afternoon, sir.
Good afternoon, everyone.
Good afternoon.
So, my topic. Can you view my screen?
Yes, sir, but not in the presentation mode.
Okay. Is that fine, ma'am?
Yes, now it's okay.
Okay. So, very good afternoon to one and all present here. I am Dr. Moliswaran. So, first thing I would like to thank for this opportunity offered by IEI and Dr. Kannamal ma'am, Dr. Baby Kalpana ma'am and team. So today I was assigned a topic called AI architectures for digital twins, cyber physical systems, and scalable data engineering. Under that, we are going to understand reducing model drift in critical CPS system, that is critical cyber physical systems. Okay. So first, to introduce what is uh, cyber physical system, as the previous speaker already explained what cyber physical system. Anyway, I would like to just give an overview on what is cyber physical system, then we'll move on to the topic. So we all know that it's a system typically integrated with software, AI, and computational models. All these things will be associated or connected to devices, vehicles, sensors, industrial machines, etc. So anything that is all which will work in a collaborative manner, which will be integratively working in a very orchestrated manner, we call it as a cyber physical system. So in this context, we are going to understand a serious issue, what you call it as model drifting. So this has been encountered during any implementation, real-time implementation of cyber physical system. So when we try to deploy a real-time cyber physical system, definitely we would encounter this issue, and we have some mechanism, or we have some strategical methods by which we can able to defend the model drift, or we can able to reduce the model drift by using some methodologies, okay, or some using some mechanisms, we can able to reduce it. So for that, we will first try to understand what is digital twins and physics based simulation model, because these two are important uh, for uh, uh, for real time simulation. That is, when you try to deploy a cyber physical system in real time, definitely you should create a similar miniature model, what you call it as a simulated model. That model should be thoroughly understood, then only you can able to build a real-time system. So to understand this, we'll try to know what is digital twin. So in short, digital twin, as sir mentioned, it's a replica of a real-time system, where if you have a real-time system machinery, you will have sensors associated with it, and you will have some devices, you will have computational systems, all integrated in a collaborative environment that will be simulated by using some simulated versions. Okay, that is simulated model we'll have. and based on that, we'll try to control the real-time system. So that twin that has been created as a digital twin will try to know the parameters of the real-time system, will try to control the actual system. So from digital twin, we can able to have full control over the real-time system. That is the intention of creating the digital twin. And one more thing is, by using physics-based simulation model also, we can able to do this process, where the physics-based system will have some extra advantages. That is, there is a specific model called as PINN that we'll be discussing in the further slides. So that model have some advantages over the existing model, that is nothing but surrogate model. So the surrogate model we'll try to understand. Before that, we'll know what are the causes of model drifting. So before that, what is model drifting is the actual system will produce some predicted output, and the digital twin which we have created, that will produce some other output. So the deviation or the value change that has been impacted during that process is been calculated, and that is what you call it as a digital what you call it as drift. Okay, so in this process, um, what is the causes for the drift is categorized into four types. The first thing is unmodeled dynamics. So where complex real-world behaviors that are absent or oversimplified in the original model specification. That means that the real-time system will be there. So when we try to create a digital twin, we will not mind about a specific complex system that is in the real-time system. So we might have ignored that, or for simplicity purpose, we might have taken it in a simplified manner. So because of that reason, there will be some issues that may cause a model drift. So this is one reason. And the second one is sensor noise and bias. So this is caused by measurement inaccuracies. That is, the measurement inaccuracy is nothing but the value that is being generated will not be accurate all the time. And what is the reason is it may have some noises in the value, or sometimes it may lead to an error. So that value will impact an error, and that error may lead to some failure in the system. So because of this, we may experience a model drift. And third one is environmental variability. Environmental variability is the third cause, where shifting external conditions, that is, because of the external conditions like temperature, load, humidity, etc., there will be some parameters which will be influencing the input value. So that is the third cause which will generate a drift. And fourth one is system aging and wear out. So this is nothing but due to the system aging. That is, whatever the twin that we have created, that might have that might be running without calibration. Okay, so without calibration, if it runs for a longer period of time, then it will show an error value, obviously. So this, for this reason, there will be a model drift. So these are the four reasons where we experience the model drift. So we'll try to understand the models which will really address this model drift in real time. So first thing is surrogate model. So before going to the surrogate model, we'll try to understand how the data in CPS system is being processed in sequence. So we have some layering approach here. So first thing, as you can see the illustration, physical system is the first layer, where the actual sensor data is been collected, or it has been obtained from the real-time sensors, and it has been processed to the next level, and it will be driving some energy. That is, it will be converted to an energy by actuators. So any sensor value, it can be typically in any format, uh, and that will be converted into energy by using actuators. So this is the first layer. And further, coming to the next layer, whatever the data obtained during the uh, that is after the actuators generates an value, that value will be fed into the edge gateways where the actual data is being processed. It will start processing now. By using some communication protocols or network protocols, we'll try to accumulate the data, and we'll try to group the or segregate the data, and we'll feed into the next layer, that is into the cloud layer. And that is the third layer called as data management layer, where the data that whatever is accumulated will be converted into uh, or it will be grouped, or it will be stored in lakes, data lakes, or data clouds, etc. Okay, so in cloud storage, the data will be segregated and stored. So whatever the stored data, we need to process, and we need to make sure that the data is being cleansed at the next level. So next level, what you call it as modeling and prediction level, is the actual level which is used for modeling the data. Just we want to use some modeling methods by which we can able to train the system, and we can able to cleanse the data at the other end, and we can feed the data into the model system, and after validation and other things sequence, we can able to fetch the expected outcome of the data. So this is being done in the next level, and based on this, we'll have some prediction value, and this predicted output, whatever we obtain, should be it should be exactly matching the real-time system. Okay, so that is the actual output. Actual output generated by the real-time system should be actually matching with the predicted output that is generated by the machines. So in this context, definitely there won't be a perfect match. Okay, so there will be some deviation in the value, and for this reason only, we are going to uh, precisely train the machine, and we can able to achieve the accuracy level whatever we expect. Okay, so for this, we are going to use some methods, and whatever the data that is been obtained at the fourth level, predicted data, that we'll be applying for various applications in real time, and we'll be using that has been explained in the fifth level. And finally, the drift monitoring will happen in the next layer only. By using surrogate models and pin models, we are going to predict the drift. Okay, so whatever the drift that we have obtained, we're going to reduce that, or we're going to make sure that the drift has happened, and we're going to reduce it. Okay, so that is the next level. So first thing is surrogate model. So as I mentioned, surrogate model is uh, an approach which has been derived from the neural networks system. Okay, so as you all know that neural networks is a deep learning model, and that is being used in this surrogate model, where the input layer is being generated, and we are going to use the hidden layer and the output layer for mapping the input to output. Okay, so that is how the details will go on. And you all know the process of how this mapping happens, and you know the computations happens in the hidden layer, and inputs, whatever the input that is being fed from the input layer, it will be going into the hidden layer, and that will be processed as output in the next level. And the key features about this surrogate model is it is purely data driven, and no physics has been required here. And whenever you want to perform any computations and you need to have a good computational speed, then you prefer to use this surrogate model as the best one, because this will help you to uh, compute the values in high speed. Okay, so that is the advantage of using the surrogate model. And the accuracy level is approximate only, not that it will be completely accurate, and there will be some deviations in the value. Okay, you cannot assure that this is an accurate output. Okay, and there is some limited extrapolation ability. That means that you cannot able to completely depend on this particular model for certain applications. And coming to the techniques, we use the general techniques, whatever is adapted in deep learning model. And advantages, it dramatically reduces the computation time, and it enables real-time analysis and monitoring. That means that the computation time will be drastically reduced. And apart from that, you can have this real-time analysis. That is, the data that has been obtained from the sensors are all real-time data, and that data is being fed into the this surrogate model, neural networks model, and that output whatever we obtain, that is a real-time analysis, or what do you call it as real-time output. Okay, so that is why this is advantages. So what is the thing is, like, we need to cleanse the data before feeding into the system. So that is the only thing we need to do. And third advantage is it supports optimization and design exploration. So we have some optimization techniques or methods by which we can able to obtain the optimized results. So by training the model again and again, retraining the model, we make the model to make the system still fine tune the system, and we can able to obtain the expected results, whatever we expect as a accurate result. And the limitations are, it requires large volume of high quality training data. So obviously we need to have a large volume of data. That too, high quality data means the data should be obviously in numbers should be more, and it should be cleansed properly. Like, we should not have duplicates, or you should not have redundancy of data, etc., etc. And and it shows poor performance outside the training range. So automatically, when you go for deviated results, if you are looking into some deviated results, it will be like poor performance only. So no guarantee of physical consistency. Predictions may violate governing laws. So there is no guarantee for anything that has been executed and obtained as results. Okay. And coming to the complete architecture of surrogate model. So we have seen what is surrogate model. So you can see here in this diagrammatic illustration, first advantage of this surrogate model is it is used for real-time prediction, as I mentioned. Uh, Next thing is it can replace expensive high-fidelity models. That means that the computational cost, whichever uh, model that is previously used before surrogate model, that been replaced by this model. The computational cost is somewhat less when you take the surrogate model. So that is the real advantage of using the surrogate model. And the operating conditions and the output response, all these things are advantages of the surrogate model. We can able to visualize the, or we can able to predict exactly what we are going to obtain as the output. So second thing is data set and pre-processing. As you all know, that the raw data that has been obtained from the sensors will be cleansed, it will be normalized, and whatever the process that will happen for pre-processing, it will all happen. And finally, the cleansed data will be fed into the model. So here, the actual neural networks will work, where the input value, as I mentioned, input layer, then hidden layer, which will be computing the entire thing, and finally the output layer will be there. So you can have many hidden layers in between to reduce the complexity of the computation. So after that, we can able to train and validate the system. And you know how this is happening. Like we'll try to take the data set and we'll try to separate into 70/30, 80/20, something like that. And we'll try to train and validate the thing, and we'll try to test it the next level. And if we don't get the accuracy, again we'll try to retrain the model, and we'll try to achieve the maximum result whenever required. Okay, and finally we'll apply this value or this trained value to the deploy real-time system, where the real-time system, when it is being deployed, it will be like a surrogate model will be running in a real-time environment, and parallelly real-time system will be started. Okay, and we can able to have control, or we can able to switch to any components in the real-time system, and we can able to see what is the current status of that particular system. All these things can be done in the digital twin, whatever we have created as a surrogate deployment model. So after deployment, we can able to connect this surrogate digital twin model to any backend, like a cloud. We can able to connect. We can connect to the APIs, whatever we want to run in the real time. We can able to do anything possible in the surrogate deployment model. Okay, so that will make an impact on the real-time system as well. So that is how we try to synchronize the operations between the twins. That is the digital twin and the other real-time twin. Okay, so this is how we try to uh, control or make decision making, or monitoring or anything like that. We can able to do it by using this twinning process. And finally, the workflow is been detailed in below in the diagram. You can see the sensor data has been processed, and surrogate model inference will be there. And after that, predicted output will be there. And finally, the applications which will be requiring the data will be using that data, and the actions or decisions will be taken finally in the final stage. Okay, and this is the next model, uh, which is an alternative for surrogate model. This is an enhanced version. You can say like it's a next level version of surrogate model, where we'll use the surrogate model plus some physics constraints, some physics laws will be applied in this model, so that we can able to get a better result. So that is the key idea of implementing this model in real time. This is also a neural network based model, where the principles, whatever we saw in the previous model, in surrogate model, the same principles will be applied in this model. Apart from that, you will have some physics equations and standard laws which will be deployed in real time to make the model still stronger, and to obtain the results in a better way. Okay, so that you can increase the accuracy of the output, whatever is predicted output. Okay, and here general terms are being discussed, like inputs, how we use in neural network, how the input layer, then the hidden layer, all those things stuff will be discussed. And neural networks, you know that how that works. It acts like a neuron, our brain neuron, and it will try to run in a very smart way to fetch the output predicted value. Okay, and we'll use two things: activation function and loss function in this context, where the activation function will actually generate some output, computational output, and the loss function will generate the loss, that is the real-time loss that is happening in the system. Okay, so this can be easily handled, and we can able to still precisely make this system, or we can able to train the model further to make it a better system or better model. So this is how the pin model resembles like. So you can see here from the left side, the observed data, we have some plots for the labeled data. That is, assume that we'll take a simple example where in a nuclear power station, a big iron rod is there. Okay, so in that iron rod, we want to extract the temperature of the iron rod when we need to raise an alarm when the iron rod temperature exceeds some threshold value. So assume like this. So we can place some sensors in that iron rod, in some parts of iron rod, and we can able to get the values, obtain the values from the iron rod. At the same time, uh, whatever the values obtained, say for example, it is of 20 meters in length, and you fix the sensor at each 5 meters. So you can able to fix four sensors, and from the four sensors, whatever the value obtained, we can able to get a set of labeled points. So that is the first thing. And the second thing is collocation points. Collocation points are nothing but the unlabeled points in the domain. That means that there will be some parts where the heat cannot be predicted because the sensor is not been present at that point of the rod. Okay, so that is what you call it the remaining points. So those points, how we can able to predict the values of the heat of the rod at that point of the rod means we can use the heat equation, physics heat equation that has been standardized in physics, and that equation will make you to generate a possible value that can be obtained at that point of time. Okay, so by using the sensor values, we can able to predict the other values as well. So that other values are put together in the collocation points graph, and those values are being called as a collocation points. Okay, so we'll be getting some if we, for example, if you're getting some 100 label points, then it will be like 10,000 collocation points. So that is how the generated value or predicted value will be by using some standard physics equation and physics laws, we can able to predict the heat value at that point of time. So that is being generated, and both are fed into the neural network system, and we know the system how it works. And finally, we will generate something called as physics residual. That is the value that has been obtained after the prediction will be called as physics residual point or physics residual output. Okay, so this is with respect to some functions. So there will be some standard functions used here to predict this output. Whatever the output that has been generated will be obtained by using some physics equations, and we'll be keeping these equations for further usage. Okay, so and next we'll calculate the loss components, because loss is very important, where two types of loss is being used, and automatic differentiation will generate data loss, and the values obtained from residual computation will be generating the physics loss. Okay, so both loss are been total put together, and it has been considered as a total loss, and this total loss we are going to address this loss only, because the loss function is very important for any system to be getting an accurate value. So after the loss function is generated, and once we obtain the loss value, then we'll go for training the actual network of system, and final output will be generated. And what is the total loss that has been obtained? What is the key highlights for that loss is like respects physics laws by construction, and it has some works with small noisy data sets also. We can able to predict any kind of loss, and the loss whatever calculated, it's all been generated by physics laws. That's why we try to use this physics laws to generate the laws. Okay, that is in the previous system we don't have this unlabeled points, but here we can able to predict this unlabeled point value, and by using the unlabeled point value we can extract the a better result or better accuracy when we use this system. So this is about the uh, pin architecture, and this is a key difference between the surrogate model and pin architecture. So you can see here the relationship is very simple. Surrogate model works like a typical neural network model. Okay, but when you add some physics components or physics laws and other things, if you add to the surrogate model, then that is called as a pin model. So next, we are going to correct this drift. So whatever the drift that has been obtained after applying these models, uh, we'll be expecting some drifts. So those two models will exactly generate some drift, and based on the drift, we are going to correct it. So this correction can be done easily by monitoring the system continuously, detecting the parameters of the system, and update the system whenever required. And finally, we can able to achieve the accuracy by adapting to the existing real-time system. Okay. So the drift, whatever that has happened in the digital twin, that can be predicted easily by using either of these models. And finally, the drift can be corrected by updating and adapting to the real-time system. So this is how we see the uh, okay. So overall, whatever the things, whatever we have discussed, this will be completely summarized in this slide, uh, where the data and context inputs are being taken from the physical sensors and physical systems, whatever the devices, the machines, whatever we have. And from there on, we'll try to apply this hybrid model engine, where surrogate model is there and physics informed model is there. So these two models can be used in hybrid manner as well. Okay, so hybrid manner means we can combine these two models where the advantages and disadvantages can be matched with each other, and we can able to use the hybrid environment for getting a better result. So after obtaining the expected outcome or predictions value, we can able to apply this in the real-time system, and we can test this in the real-time environment. The real-time system can be any of the domains, like it can be an autonomous environment, autonomous automation system, or autonomous vehicle management, or it can be in healthcare monitoring, or it can be anything. Just for your understanding, I've discussed two case studies here. So first thing is autonomous vehicle system. An autonomous vehicle will contain some set of sensors like lidar, cameras, radar, etc., etc. All the sensor value will be obtained and collected when the car is autonomous car is moving on the road, and the data that has been obtained will be in various formats because lidar is a 360-degree what you call it as a laser based system, so that will generate some format of output. Similarly, camera will generate video output, and similarly, radar will generate some other output. So all this output that has been generated will be accumulated, and it will be processed to the next level. So the perception task is to understand the data formats, understand the in which format the data is there, and it will try to uh, make decisions intelligently by using the further processing, where the perception task is to first clearly segregate the data and feed the data into the hybrid model architecture. And from there on, the predictions will be happening in the next layer. And the based on the predictions, the vehicle can do some decision making. That is how the real-time system will work when an autonomous vehicle is moving on road. So here you can see uh, the speed control or the lane mannerism or path planning, in which path it has to go, or the brake when it has to apply the brake. All these things are being managed by intelligent decision making system, which will be running inside the autonomous vehicle itself. So for this, uh, all this that is the hybrid model architecture or predictions, all these things will be incorporated or embedded inside the vehicle itself, and based on that vehicle running and other things, the decision will be taken instantly. So this will happen within seconds. So like human beings, how they think and make app decisions, the app time. Similarly, here also the predictions will be obtained, and it will be processed in a very micro level in milliseconds and microseconds, and final outcome will be generated at this layer. So this is a typical sequence in which the outcome will be generated finally, and whatever the car system has as an intelligence system will be dependent on this prediction model only. Okay, so this should be precisely generating the output, and based on the precise output generated value only, the vehicle can able to sustain the decision making. Okay, so next thing is just I've chosen hospital management system. Here also it's very important that we need to have this hybrid model incorporated in the hospital system, where the data set will be your EHR records, electronic health records, and these records will be processed, and it will be separated, grouped, or it will be processed. Based on the processing, we'll be trying to make some decisions. We can able to do an automatic operation, robotic surgery. All these things are being dependent on the proper training of the machines, and the output that is being generated from the predicted system. Okay. So with this, the next level scope is like we have a lot of scope in this model drifting area. So research scope is wide, and you can just explore the things properly, and you can have an idea on what is actually happening. So these are some possible domains in which the model drift can happen, and still we are facing the challenge. We couldn't able to exactly match the things properly. So if you try to overcome these challenges and if we make an optimized system, definitely we can able to build a better smart system in real time. So I profusely thank Dr. Kanamal ma'am, Dr. Baby Kalpana ma'am and team and the management for giving me an opportunity. Thank you so much. Any queries?
Sir, they posted their question in tab.
Okay. Okay, the first question is how does a digital twin help in detecting drift? So, as I mentioned, you'll create a replication copy of the actual real time system in a digital format that is called as a twin, that is called as a digital twin. So, when you run a real time system, you will have machines, you will have sensors, etc., etc. So all those things will be getting you'll be getting some output at that level, and at the same time, if you have created a miniature digital twin on the other side, and if you run that system, you cannot expect the same output, whatever that has been obtained in the real time system. That same output will not be there in the digital twin as well. So that is how the drift will happen because of many reasons. The drift may be caused by many reasons. As I mentioned in the earlier slides, there are four main causes for the drift. So because of that reason, it may get a different value. So it is up to you to manage the drift by using this surrogate model and pin model. So that is what we have discussed so far now. Hope I have answered the question. Uh, Sir, you mentioned that surrogate models need a large amount of high quality training data. The available real world data is limited. How can we still build an accurate model? Okay. So surrogate model need a large amount of high quality data. But you have an alternate option called the pin model, where even if you have sparse data, you can able to use that model. A surrogate model is limited to large volume of data because in such a way it has been designed. Okay. But even if you have a sparse amount of data, you can use a pin model because that is better than the surrogate model. So that is an alternative. Since the predicted output may not exactly match the real-time output, how do we decide what level of prediction error is acceptable in the real-world system? Okay, so this is a crucial question. Uh, Predicted output may not exactly match with the real-time output. Obviously, it will not match most of the time because a real-time system always like it will be influenced by many parameters. Okay, but if you take a digital twin of the same system, it won't be same as the real-time system because we might have replaced something in the digital twin model, or we might have made a miniature version of the real-time system. So like that, we'll be having some deviations. So because of that, we'll be getting some errors or drift will happen. Okay, so we can easily we can able to minimize the drift uh, by training the model continuously, so that if we train the model, you might have studied about like how this deep learning works. uh, when we use the neural network thing itself, we'll be training and validating and then test it. Okay, so when we don't get that expected output, what we do is again we'll retrain it, again we'll try to run the same thing, right? So this is how the thing will work. Say if we run one epoch means like one forward and backward complete cycle of the data training, train the data set. If you run it completely, then in one epoch, if you don't get the result, we'll go for the next epoch. So that is how the epochs will move on. I think that is the answer for the question. And what is the role of sensors and actuators play in model drift? See, actually, sensors are going to collect the raw data from the environment, like temperature, pressure, or anything like that. So that raw data will be driven by actuators. So the raw data, whatever that has been obtained, will be collected by the sensors, and it will be pushed to the next component, that is nothing but your actuator. Okay. So when we try to get the data and when we try to process at the next level in the actuator, mostly the data, whatever is obtained, just like that, we cannot be able to process it. Okay. We need some fine tuning of the data. So that is how the real-time system and the digital twin will be varied. Okay. So there, when we try to fine tune it automatically, what happens is we may lose the integrity of the data. So that is why we should not like we have to ensure that the data loss is minimum, and with the minimum data loss only we can able to achieve the things whatever is possible. Okay, so we should make sure that the minimum data loss is happening, and we should not cleanse completely. Like there will be some essential data, there will be some non-essential data. We have to segregate it properly, and we need to process the data. Then only we can able to feed that into the real-time system to get the expected output. Hope that is fine. How does a surrogate model support digital twin systems? As I mentioned, surrogate models are going to obtain the sensor data in the real-time CPS system. It is going to process the sensor data, and it is going to generate some output at the output layer. And finally, if the prediction model makes an incorrect decision in the application, like self-driving cars or robotic surgery, what backup mechanism are usually used? See, when you go for robotic surgery, or when you deploy a real-time autonomous car on road, it should be tested a number of times. Only then we can go for real-time implementation. Okay. Without testing, if you claim that that particular autonomous car is level 3 car or level 2 car, like that, then it should been tested properly. Then only it can be, once if it is approved by some standard organization only, they can be used in real time. Without testing or without properly coming to the conclusion that it is uh, going to be deployed in real time, means then that will not happen in real time. And robotic surgery also. The robotic surgery, when it has been decided with some parameters, and when they train that robot uh, as you know, that robots will have this ROS as the operating system. That kind of operating system are real-time operating systems. Okay, so it has some intelligent capability which will try to know the actual condition of the patient, and accordingly it will try to manage the issues. Okay, so it is a real-time operating system which will get the live inputs from the when it does a surgery. Okay, so that is how it has been well trained. Okay, so it will not make mistakes. 99.9 accuracy will be the accuracy of the ROS. Okay, so that too, when it applies to a real-time system, it will have maximum accuracy, and that is how it has been used in normal knee replacement surgery or any other laser-based surgeries. They'll use it precisely. Okay, so precision is important. So that's why these things are very complex in implementation. That's why we are very particular about this methods, so that predictions will happen appropriately. That the predictions will be maximum possible. Okay, so in such a way we need to train the system. Hope I have answered for all the queries.
Thank you, sir. Thank you for your wonderful presentation.
Thank you so much, ma'am.
Thank you,
Thank you.
sir. I now request Gerald Felix, sir, to present the topic on MLOps for digital twins. Gerald Felix, sir, please.
So, very good afternoon, everyone. Just give me a
Good,
minute. Let me start presenting my screen. And unfortunately, due to some system error, I can't turn on my camera. But anyhow, I will present my screen, and I hope it is visible for you all now.
yes, sir, it's visible.
So once again, very good afternoon, everyone. I think it's time to say good evening. Yeah. So thank you for joining this session. Today's topic sits at the intersection of physical engineering system, intelligent server, and scalable data platforms. The title may sound broad, so let me simplify it right away. This session is about how real world systems such as factories, vehicles, smart grids, and sites can be connected to digital models, and how AI plus data engineering make those models useful in practice. I hope the speaker before me, Saga, have covered most of these things, but I am here to simplify the concepts, not going very deeper into the terms. So I want everyone to understand what is the main concept of this digital twin and other things, cyber physical system. So the audience here includes, as far I know, a mixed audience like professors and students from different engineering branches. So I will keep the session concept driven and example oriented. The goal is not to go deep into mathematical models, but to build a clear understanding of the architecture, the workflow, and the opportunities for teaching, research, and student projects. Think about a college campus where we know the status of power usage, water pumps, buses, and lab equipment in uh, real time. This is the kind of system where digital twin becomes very meaningful. So let me move on to the next slide. So why should engineers care? Let us begin with the obvious question. Why should engineers care about digital twins? The answer is that digital twin are no longer just futuristic concept. They are becoming an important tool in the industry 4.0 for monitoring, prediction, and optimization. So it's not future; it's already there in place. For example, in smart factories, digital twin helps track machine health and support predictive maintenance. In smart grids, they help balance demand and supply, especially when renewable energy sources are involved. In autonomous vehicles, they support continuous feedback and safety decisions. In smart cities, they can help with traffic flow, infrastructure planning, and resource allocation at scale. What makes these systems powerful is not only the digital model itself, but also the AI and scalable data pipeline behind it. Without those, the twin would just be a static dashboard instead of an intelligent operational system. A good example, we can quote a good example like a smart traffic system can use a city level digital twin to simulate what happens if one major junction is blocked. That allows traffic signals to be adjusted dynamically. So, before continue to the next slide, I would like to ask you people a question. How many of you start using every day you using AI? I hope most of us in this crowd, or most of us in this room, every day it's like checking the mobile. We started using AI, and we using AI for both our personal as well as our professional or educational life. So AI became a part of our life. Likewise, these technology is also uh, getting part of ours soon. So now let us define cyber physical systems or CPS. A CPS is a system where physical components such as sensors, actuators, machines, and infrastructure are tightly integrated with computational networking and control. The key idea is the feedback loop: sense, compute, decide, and accurate. The system is consistently observing the physical world, processing the data, making decisions, and acting back on the physical environment. This is why CPS is more than just a machine with software. So it's like our the systems or the applications or the machines whichever we see around us are getting intelligence. It is an active system respond to its environment. Example includes smart homes, industrial robot cells, medical monitoring devices, and autonomous vehicle. A good example is in an automated manufacturing line, sensors measures temperature and vibration, software detects an issue, and actuators slow down or stop the machine before damage occurs. So it's complete kind of a cycle taking place. Next, let us define the digital twin. So a digital twin is a living virtual representation. How many of you here have tried out using Android Studio? So in Android Studio, we have a emulator, virtual emulator, where we can. There is no need of a mobile phone, physical mobile phone. We just want to install the uh, digital, I mean, virtual illuminator. So by installing it, you can see the output, how it looks and feel in the mobile phone. It is the same similar way. A digital twin is a living virtual representation of the physical objects, process, or system. It is dynamically updated using real time data from physical counterpart. This is what makes it different from a traditional simulation. A simulation is usually run for a specific study and then they stop. A digital twin stays connected to real assets over time and continues to evolve through its life cycle. Because of that, digital twin can support continuously monitoring, what if analysis, prediction, and optimization. In simple term, it acts like a digital laboratory for a physical system. I would like to quote a few examples to make it even more clear. Okay, nowadays when you want to get a license, four-wheeler license, or especially four-wheeler license, and if you approach any of the driving school, reputed driving school like Maruti Suzuki, they not immediately made you to shift in their own vehicle, in their real vehicle. They will put you in a simulation where they will give you some practice and training, like how the steering you need to work, how you need to use the clutch, pedal, accelerator, changing the gear shifts, everything they will teach you from the simulation. Then they will move you to the real vehicle. So it avoids, first thing it's, you will get a feel of how it really look when you drive a vehicle on road. And the second one is it reduces the damage for them. If you directly get into a real vehicle, and if you really don't know what to do, and if you hit some person, the damage is really high. To avoid those kind of things, uh, it is really very helpful. Likewise, in industry, so for example, a wind turbine digital twin can continuously receive rotor speed, temperature, and vibration data, and use that to predict where or optimize energy generation. So it's safe cost, and it also save people who work on it. This slide explains the relationship between CPS and digital twin. So far we understood what is CPS and what is digital twin. A simple way to present this is CP is the physical nerve system and muscles, where the digital twin is the digital brain and analytical engine. The physical CPS is responsible for sensing and acting in real world. Sensors collect data, communicate, networks move data, and actuators carry out control decisions. The digital twin takes the data, contextualizes it, runs simulations or machine learning models, and recommends or directly applies optimized actions. So the twin does not replace the physical system. It never ever replaces the physical system. Instead, it acts as the system virtual proxy, making the physical system more observable, predictable, and controllable. Even I will give you another example. If anyone of already worked with cloud, in cloud we can create virtual machines. The term virtual machine means it have everything you need, but it don't have the physical system in your hand. But you can just input your username, password, and when you hit a sign in button, it will automatically open your beautiful Windows machine or Ubuntu machine. So it is not physically, you can't see it physically with you in your line on your disk, but you can get all the you can use it as like a physical system. For an electric vehicle, the physical CPS includes the battery pack, sensors, motor, and controller. The digital twin can estimate battery health, focus degradation, and suggest optimal charging strategies. Here we have a simple reference architecture. This slide presents a simple reference using 4 layers. So we have a very useful 4 layers. This is a very useful teaching model because it makes the system easy to understand. I hope my previous speaker also covered a lot about it, but I'm here to make it simple and to reach everyone. So At the bottom is the physical layer, which includes machine, robots, vehicles, and physical infrastructure with sensors and actuators. Above that is a connectivity level layer, which contains gateways, PLCs, communication protocols, and industrial networking technologies. The third layer is the digital twin layer, where virtual models, state databases, and simulation engines represent the assist. At the top is the intelligent and application layer, where AI and ML models, optimization logic, and dashboard sits. So it's a complete combination of everything. A good example to understand this architecture is in a smart building, sensor detect temperature and occupancy. The connectivity layer transmit the data, the twin model room conditions, and the application layer decide how to optimize air conditioning. Now let's understand the cloud-based CPS twin. The main point here is that a cloud acts as a centralized for ingesting, processing, and storing data from many physical systems across different domains. So as we saw in the previous slides, when we speak about CPS, we want to connect the various machines. So that the information we collect from the machine need to be get stored and it need to get processed, where cloud plays a vital role. The physical system can include transport, energy, water, homes, and city infrastructure. Their telemetry is sent to the cloud cyber layer, which provides scalable compute and storage. On top of that, a smart interaction controller uses AI or models to make decisions and coordinate actions back to the physical system. This is useful to explain because it shows that digital twins are not only for one machine, they can also be built at system level across domains with centralized intelligence. A city administration could use a cloud-based twin to integrate traffic, water distribution, and street lighting data in one place for a better planning and operation. So it's all under one roof. Now let's discuss about the life cycle. Here you can see the important, uh, uh, I mean, here you can think a digital twin is created once and finalized. In reality, the twin evolves through a life cycle. The first stage is create, where the initial model is designed using domain knowledge, CAD data, design specifications, and historical data. The second stage is calibrate, where the digital models is aligned with the real system using live sensor data. The third stage is operate, where the twin runs continuously for monitoring, prediction, optimization, and control. The final stage is update and retrieve, where the twin changes as physical system changes and eventually ends when the physical access is decommissioned. The life cycle view is especially helpful for faculty and students because it shows that digital twin projects require both design time thinking and operational thinking. If a lab upgrades, a good example is if a lab upgrades a machine when a new motor or sensor, the digital twin also needs to be updated to remain accurate. What exactly does AI do inside a digital twin? So far we discussed a lot about CPS, digital twins, cloud, and now we discuss about A in digital twins. What are their key roles? There are four major roles shown here. First, predictive model, focus future system behavior such as remaining useful life or energy consumption. Second, anonymity detection identifies unuseful patterns that may indicate mechanical faults or cyber attacks. Third, optimization and control compute better schedules, set points or decisions. And fourth, decision support summarize complex system states so human operate can make faster and better judgments. So this is a good moment to tell the audience that AI in digital twins not just about one algorithm. Different AI methods serve different engineering goals. So an example on AI in digital twin is like in a water treatment plant, prediction can estimate pump failure risk. Anonymous detection can identify unusual chemical readings, and optimization can reduce energy consumption. Let's discuss it further with a scenario. The early concepts into practical engineering scenarios. We start with the physical assets, such as industrial motor or pump equipped with sensors that capture vibration, temperature, and current. The digital twin injects this streaming data, maintains health indicators, and use machine learning models to estimate failure risk. Based on that, the system can automatically schedule maintenance before failure or dynamically adjust operating load to reduce stress on the machine. This is one of the earliest and easiest example for you to understand because it clearly shows business value, less downtime, lower maintenance cost, and safer operation. A good example is imagine your college works up a motor that usually fails unexpectedly. If the team predicts a high chance of failure 14 days in advance, maintenance can be planned through in non-working hours instead of losing the machine suddenly. Foundation models. So every day we are using various foundation model for various use cases. Say for example, we use Nano Banana for image generation, Vio for video generation, ChatGPT 5 for text generation or creating some images, a lot more. So this slides introduce a more recent development, the use of large language models and foundation models in digital twins. One role is accelerated creation. Instead of engineers manually defining every component and relationship, foundation models can help generate twin components, physical model descriptions, and configurations from requirements, manuals, or historical data. Another role is intelligent assistance, where fine-tuned model act as conversational interface over CPS data, helping operators ask questions in natural languages. It is useful to explain here that foundation models do not replace domain expert. It never ever in any field it won't replace. Rather, they can act as assistant that speed up engineering work and make complex system easier to interact with. A good example to understand it even better is an engineer could ask which motor in this plant is most likely to fail in the next 2 weeks and why. A foundation model based assistant could summarize the relevant sensor trend from the twin. So, what are the next things? It's a data challenge, data challenges in CPS. CPS environments generate data with a classic 3 V's: volume, velocity, and variety. Volume means there may be thousands of devices generating large amounts of telemetry every day. Velocity means data arrives quickly and sometimes decision must be made within milliseconds or seconds. Just think you are, I mean, there is one medical emergency happened and a doctor who's sitting in US need to treat a patient in Coimbatore. It's a kind of a robotic surgery. And in case if we have some latency in the data, the patient will die. So the response time should be always high. And the last one is variety, means the platform must handle many data types, including time series, sensors, data, even logs, camera images, and even 3D models. The key message is that a digital twin is only as good as the data pipeline supporting it. If the platform cannot insist, process, and store data correctly, then the twin cannot remain accurate or responsive. A smart city platform may combine traffic sensor systems, CCTV alerts, weather data, and GIS model. That is a good real world example of eye variety. Even in Coimbatore, we have the GD Naidu uh, bridge, where near to Avinashi Road. So it is currently they have equipped with AI cameras and much more. So if you not wear your seat belt or if you not wear your helmet, in the screen they are also place screen in certain limitations. So you can see your vehicle number and the person name. I mean the owner name. So you need to you need to pay fine if you're not following the rules and regulations. Next comes the IoT data pipeline architecture. Here you see how raw physical data becomes usable intelligence. The process begins at the edge where physical devices and edge gateways perform initial filtering or protocol conversation. Then the data moves into ingest layer through brokers such as MQTT or Kafka, which decompose data. So let's have a good example for this. For a fleet of bus, edge service, edge devices send GPS and engine data. The broker collects the streams processing engines and compute delays the fuel metrics, and the twin provides a live fleet view. And we have it into the last slide. So let's understand a little bit about Lambda and Kalfa, then we go on to the conclusion. The batch layer stores the master dataset and computes high accuracy views from historical data. The speed layer handles incoming data streams in real time and provides fast updates. The serving layer combines results from both so users can query complex view. In an energy management system, the speed layer can show live consumption anonymous, where the batch layer can produce accurate monthly efficiency reports. Next comes the kappa. Now, compared with kappa architecture, kappa treats all data as stream and uses a unified event log, often through a platform like Kafka. Instead of having a separate badge and separate speed layers, Kafka relies on one streaming processing pipeline to compute both real-time outputs and recomputed historical views. So here we have the different states. So the future wise, you already have heavy badge analytics and need extremely accurate long-term reporting. You need to go with Lambda, and real-time streams dominate, and you desire a signal unified code base. You need to go with Kalfa. So we came to the last slide. There are also many accessible campus scale twin projects. One area is human in the loop digital twins, especially for safety critical domains where humans and AI need to work together. Another is cybersecurity twins that simulates and detect cyber attacks in CPS environment. So it's not just we are implementing things, we also need to keep on monitoring and ensure safety. So this is the final slide. CPS gives us the real world systems with sensing, computing and control. Digital twins gives us a live world, live virtual representation that supports prediction and optimization. AI and scalable data engineering make the twin intelligent, responsive and practical at scale. The best way to close is by shifting the focus. Uh, in digital twins are not only a research buzzword, they are practical architectural idea that can bring together multiple branches of engineering in very meaningful way. So we came for a conclusion. I hope this session give you a broad understanding and knowledge about what is what. Thanks a lot for this opportunity, Kalpana ma'am and the management team. People, if you have any questions, you can feel free to ask.
Sir, they posted some questions.
Thanks for letting me know, ma'am.
Yes.
Uh, Unfortunately, I can't see questions in the chat.
Sir,
Okay,
you
let me
please
see
check
okay, everyone.
Q&A, sir. You please check Q&A.
Okay. Yeah, okay, 1 second. Q&A. Yeah. Do I need any special software to implement digital twin for cyber physical systems? Latency is critical. Just a moment, ma'am. I'm just going through all the questions so that I will answer all at once. What else? How does IoT support in digital twin technology? So for the first question, it is not necessarily we can start with normal IoT platforms, cloud services. We don't need anything very specifically for it. And um, for the second question, for cybersecurity, physical latency is critical. How do you balance cloud AI processing with? So it's an excellent question. In real world systems, we use the hybrid architecture. Critical real-time decisions are handled at the edge itself using edge AI or embedded systems. Because cloud communication may introduce delay, the cloud is mainly used for heavy AI tasks like training models, historical analysis, optimization, and long-term predictions. So edge handles instant response while cloud handles intelligence and scalable. How does IoT support digital twin technology? IoT is the foundation of digital twin. Sensors collect real world data like temperature, vibration, pressure, location, mission status. This live IoT data continuously update the digital twin model in digital environment. Without IoT, the digital twin becomes only a static simulation instead of a live intelligence system. So IoT is much important for it. And in your option, what is the most important soft skill for engineer building AI system? In my option, the most important soft skill is responsible and empathy, because when we build a AI system, we should first understand human problems, emotions, workflows, and real world needs. AI should augment humans, not just automate everything blindly. If you go and automate a neurosurgeon as a AI, then yeah, everything our work all we given to AI and we will sit simply. So it is not idea. We need to put AI in places where there is really a necessity, where a human cannot do work things. I think I have answered for almost everything.
Yes, sir.
There are also a few more questions, but I
The
think due
last two
to
questions, sir. The last two questions.
what is the biggest challenge in implementing
Yeah,
digital
yes, sir.
twins?
Yes, sir.
And what is the other one? Now, scalability. So, what is the bigger challenge in implementing digital twins in real industries? And one more question, can one digital twin be used for different machines, or does each machines need its own? Okay, in safety critical systems, we never depend on a single AI model or a single sensor, and most importantly, um, it is completely dependent on the machines which we going to implement it. But there are possibilities where we can use the digital twin for different machines. We can create a kind of a template where we can use it in various machines. And whenever we use to implement it, we also need to ensure that the data is not duplicated, and the information whichever we collect from that one digital twin is not duplicated, or data loss on the other system. And how scalability achieved in the digital twin system? Scalability is achieved using cloud computing, distributed data processing, IoT platforms, and microservice architecture. Instead of processing everything in one system, workloads are distributed across multiple services and cloud resources. And edge computing is also used to reduce cloud load. It's again a same kind of a repetitive answer. Edge computing is also used to reduce cloud load and improve performance. For example, a smart city digital twin may handle millions of sensors reading by distributing processing across cloud and edge systems. I believe that I have answered for most of your questions and really very sorry because we are running out of time and your ma'am asked me to complete it by 4:15, but now it's almost 4:28.
Okay, sir. Thank you so much for your wonderful presentation. Now
Thanks
I
all.
let, thank you, sir. Once again, I thank you all our speakers. So now over to Pradeep Kumar, sir, for vote of thanks.
Good evening to all of you. Am I audible?
Yes, sir. Audible, sir.
Yeah. So it gives me immense pleasure to propose the formal vote of thanks for this IA technical webinar on AI architectures for digital twins, cyber physical systems, and scalable data engineering under the aegis of Computer Engineering Division Board, IEI, organized by Institution of Engineers India, Coimbatore Local Center, in association with the Department of Computer Science and Engineering, Sri Shakti Institute of Engineering and Technology, Coimbatore. At the outset, I extend my sincere gratitude to the President of IEI, Chairman of Computer Engineering Division Board, members of Computer Engineering Division Board, Council members, and Saurav Dasgupta, Executive, IEA Headquarters, for their constant and continuous support of all our activities. On behalf of IEA Coimbatore Local Center, I extend my heartfelt thanks to today's esteemed panelist, Mr. Prakash Kamaraj, Senior Manager, Deloitte, Bavaria, Germany, Dr. S.K. Maulishwaran, Professor, Department of Computer Science and Engineering, Dayanand Sagar University, Bangalore, Mr. Gerald Felix, IT Analyst, Bosch Global Software Technologies, Coimbatore, for accepting our invitation to address this program. My sincere appreciation to the Principal and Management of Sri Shakti Institute of Engineering and Technology for continuously interacting with our IIA Coimbatore Local Center and for the dedicated support in arranging various technical activities. I thank Dr. M. Sendil Kumar, our beloved Chairman, IIA Coimbatore Local Center, for his welcome address and guiding all our center activities. Special appreciation is due to Dr. K.E. Kannammal, Professor and Head, Department of Computer Science and Engineering, Sri Shakti Institute of Engineering and Technology, Coimbatore, for your efforts in organizing this program. Finally, I extend my sincere thanks to all the participants of this webinar, IIA Council members, committee members, IIA corporate members, industry members, faculty and students from various institutions for their participation. On behalf of Institution of Engineers India, Coimbatore Local Center, once again, I thank you all. Thank you.
Thank you, sir.
Thank you, sir. One last announcement to all the participants. All participants are requested to register themselves and pay a token fee of 300 rupees for obtaining the webinar participation certificate. Thank you. Thank you all.
Thank you, sir.